Hello everyone. In this video, we are practically going to implement the linear regression model without leveraging any of the scikit-learn's modules. So we are going to essentially build this linear regression model right from scratch. Before we begin with this coding exercise, let us actually look at understanding more about the gradient descent process, which is pretty much required for us to deduce what could be the right values for your model parameters, that is weights and biases. So weights are analogous to the different beta coefficients of different variables that are considered within your dataset. And bias here is associated with the intercept. If you remember, your yi hat was given as beta naught plus beta 1 x1 plus beta 2 x2 and so on till beta n or beta j xj. So where x1, x2, x3 and so on till xj are nothing but your independent variables. All of these beta coefficients are your model parameters along with the intercept, which is represented as beta naught. I have replaced these beta 1, beta 2 and so on till beta j with a weight vector which has these values of w1, w2 and so on till wj. Similarly, beta naught is replaced by this bias term. So weights and bias are nothing but the model parameters that we are going to consider optimization for. Okay. On a very high level, so this particular plot actually helps us understand the gradient descent algorithm quite a lot. If you closely observe the y-axis here, this is a loss function. The loss function is typically expressed in terms of the model parameters, weights and biases. But in this particular plot, for a better understanding, we have not considered the bias term at all, or probably bias is equal to 0 in our case. So we'll end up with having a representation of loss function only in terms of weights here. And hence this is two-dimensional in nature now. So for an initial value of W, so this is the initial W value that we have chosen at random. We are now looking at computing what the slope is or what the gradient is. So differentiating the loss with respect to W is going to help us understand what the gradient value here is. So we are going to make use of this particular gradient or derivative that we have computed in order to find what our next W is going to be. Our next W is essentially nothing but the difference of the current W and eta times, which is learning rate, eta times dl by dw, which is a derivative that we have computed with our initial weight here. Okay. So eta here is going to be learning rate, which is fixed in nature. I'm going to probably consider a value of 0.01 for now. So we clearly can understand what our next weight could be. So here we find the next weight and you compute your gradient. Yeah, that is differentiating this loss with respect to W again at this particular point. And now in your next parameter update, so this gradient value is being used. So this is an iterative process where you keep on updating your weights till you observe a minimal loss, till you attain the convergence. The convergence could essentially be when you are not observing any significant difference in terms of weights that you have obtained at the current iteration with respect to previous iteration, or the gradient that you have computed at this specific point is close to 0. And that's when you have attained your convergence and you stop this iterative process. So this is a good understanding that we have gained about the gradient descent algorithm so far. If I break this down, I can break this down into 4 different steps. The very first step is where you try to initialize your weights and biases, which is your model parameters. The next step is all about computing what your predicted y values are, which is given by this equation, which we already are aware of. And third step is going to be computing the loss. The loss is given by mean squared error, which is the difference of the predicted y and actual y values. Take a square of it. Sum it for all of the observations that you are observing. Divide it with 1 by n. So it's nothing but you are trying to find the average squared deviations for all of your data points. For every data point, you are now having actual y and predicted y. So using this formula, you compute what your loss is. So your yi hat can be expressed in terms of the model parameters w and b as mentioned in the previous step here. Cool. In the fourth step, you basically are finding the gradients that I have mentioned a while ago. That is dj by dw, or probably you can call them as doj by dw, since we are having multiple parameters now, one weight and one bias in terms of in case of having only one variable. If you are considering that you are only having one independent variable, that is x1, then obviously you are going to differentiate this loss. You are going to do a partial differentiation of this particular loss with respect to w. You're also going to do a partial differentiation of this loss function with respect to b, since there are multiple model parameters involved. So on differentiating this MSE, this equation, you are going to obtain these different equations, that is dou j by dou w and dou j by dou b here. Okay. And finally, you substitute these values in this parameter update equation so as to deduce what your next parameter value could be. Okay. So with what we have learned so far as a context, we are now going to implement all of this in Python. Okay. So let me go back to this VS Code and specifically this .py file where we are going to write this particular class called linear regression. So let me define a class called linear regression. And very first step here is going to be defining the constructor. The constructor, which is the init method here, basically considers different parameters like learning rate, the number of iterations that we are supposed to conduct, so on and so forth. So the learning rate, I'm providing a default value of 0.01 or 0.001. And the number of iterations here is again going to be 1000. All of these are default values. When you're trying to instantiate this particular class, you are supposed to provide any of the values for any of these parameters. Those values will override these default values that I have provided here. Okay. So similarly, we also have weights and biases. So if I'm not providing any values, it's going to throw an error since its previous parameters are initialized with some default values. We are also supposed to initialize these weights and biases with some default values. So I'm considering none for both weights and biases here. I'm going to assign the learning rate to self.learning rate. Similarly, the weights I'm going to assign to self.weights. I'm going to attach all of these parameters to the object itself. Same is the case with the n iters, which I have not done yet. So n iters should be assigned to self.n iters, which is the number of iterations that you're planning to conduct for your optimization process. So you are pretty much aware that you need to have both fit method as well as predict method whenever you're trying to create a model or trying to implement the model training process as a whole. So we are going to define both fit method as well as predict method here. For fit method, we always make sure that we are providing the train data because we are going to make use of the train data in order to do the learning process. So the model training process typically involves both X-train and Y-train data here. The predict process could potentially involve the X-test itself. So whenever you're planning to do model evaluation in terms of understanding what is the deviation of model performance or model evaluation metric in between train and test, you might supply X-train as well in order to generate the predictions for your train set. But that's a different case altogether. In the current implementation, we are going to consider the test set observations for getting the predictions for. Okay. So in the fit method, we are now going to assign X to self.x, or we need not do that. So at the very first step, I'm going to understand what the number of samples are and what the number of features are within your X data. So X.shape is going to get me the total number of samples that are part of the training set and the total number of features that are part of the training set again here. Okay. So the very first step in the gradient descent process that we have learned here is to initialize the weights and biases here. So let us initialize the weights and biases. Initialize the weights and bias terms or bias parameters. So I'm going to initialize all of these weights and biases with values of 0. So the number of weights will be same as that of the number of independent variables that you are having within your data. If you closely observe, so there are as many number of weights that there are within this equation as the number of independent variables are. Okay? So that's what I'm going to do here. So I'm going to initialize all of them with zeros. So the number of features here is going to be n features, which I'm providing within the parenthesis here. So this is my weight vector, the initial weight vector here. I'm going to assign this to self.weights, which is now initialized with zeros here. So self.bias is a single component, right? It's a single term. It's an intercept term, which is given by b here. I'm going to initialize this with 0 again. Right after initializing this weights and biases, that is step number 2 here within the linear regression optimization process, you are now going to find what your predicted y values are, which is given by W transpose X plus B, which is a linear combination of your X and weights along with the intercept term, which is bias here. So y preds here is going to be the dot product of X and W, that is self dot weights, plus the additional bias term that we have initialized in the previous step, right? So we have now computed what your y parades are. So once you compute your y parades, so you're now going to find or differentiate the loss with respect to w, which is given by dw, and differentiate the loss with respect to the bias, which is given by db, so that we obtain what the gradients are. So once we obtain what the gradients are, you can update the parameters w and b respectively. The formulas for these gradients are given here within this particular slide. So on differentiating this loss function, with respect to w, this is what we obtain. And on differentiating this loss function with respect to b, this is what we obtain. So we are now going to implement this here within Python. So here it's going to be 2x, that is a dot product of x and the difference between predicted and actual y values. So simply I'm going to consider the dot product of x transpose and the difference between predicted and the actual y values, right? Which is given by y here. So dot product is going to take care of the summation part, because whatever products that we obtain here in between x transpose and y parades minus y, all of them are summed up by this particular function itself. So we have not defined this numpy at all, so we have not imported it yet. So import numpy as np. Now we clearly have this summation or the sum of different products that we have obtained here. So we need to also multiply that with 2 and divide it with 1 by number of samples. So let's multiply that with 2 first, and also divide this whole term with 1 by n. N here is going to be the number of samples that we have reduced in our initial step itself. Cool. So same is the case with identifying the gradient for bias here, except for the fact that we are not going to do any dot product since there is no x involved here. We're just taking the summation of all of the differences that we observe between y parade and y. That's all. So we're just taking the sum of all of these differences that we are observing. So np.sum is going to produce all of those resultant sum of differences here. We are going to again multiply this with 2 and then divide with 1 by number of samples. And that's it. So we have now calculated what your dw and db could be. And once we have done that, we are going to update the parameters by using the parameter update equation. So what is a parameter update equation? So it's going to be self.weights is equal to self.weights minus eta times. Eta is going to be the learning rate here. Eta times dw that we have computed in the previous step. So for bias update, self.bias minus eta times db that we have computed in the previous step. So we now have updated the weights and bias, but only for once. So we need to conduct this iteratively. You remember we have actually conducted this whole optimization process iteratively till we observe the minimal loss. So we are going to update our weight and bias n number of times. Okay. So we clearly are now going to include this in a for loop. So for iter in, number of iterations is defined here within your init method itself. So I'm going to include this as a range object. So we are now having 1000 different iterations that we are conducting. So there are 1000 times that we have updated weights and biases. At the end of 1000th iteration, we now have the updated weights and biases. Okay. So using these weights and biases, we are now going to compute what your predicted y values are within your predict method. I'm just copying this whole statement that we already have built in the previous method to the predict method here. It's nothing but the dot product of x and weights that we have computed. So the weights and biases here are nothing but the weights and biases that we have identified at the end of n iteration, that is end of 1000th iteration in our particular example here. So we are now going to return these y parades that we have computed within the predict method. So we have now built this linear regression class as such. We are now going to make use of this particular class and try and create an object specific to that particular class. Let's import it first from regression, that is from the module that we have specifically written, which is regression.py. We are going to import the class called linear regression that we already have written. So we'll make use of this particular class, instantiate this particular class and call the model object as model. So we are explicitly going to define the learning rate here as 0.01. I'm going to leave all other parameters to the defaults that we have defined here. So n items is here is going to be 1000. Weights and biases are now initialized with none values. I'm going to leave them as is. So we have this particular model object now. I'm going to invoke the fit method with the train data as we have discussed earlier, which is x train and y train. So once the model is fitted onto the train data, we're now going to generate the predictions pertinent to the test set. We call this as test predictions here. Okay, so we'll have to restart the kernel since we have written a lot of code within this regression.py module. So once we have restarted, I'm going to run all of these cells. So we now have generated the test predictions as a whole. Since we have generated the test predictions and we also have the y-test data, we're now going to identify what could be our MSE and RMSE values, which are the evaluation metrics for the regression case that we are trying to solve here. So in order to generate the evaluation metrics, I'm going to define a new function called MSE, or probably I'll write it as eval metrics, okay, which considers both the y-test as well as test predictions that we have defined, okay. So we'll take a difference of these two. You remember the MSE formula properly, so we're just taking the difference of the actual and y-preds, square all of them. Once we square all of them, you're going to take sum of all of them and also divide it with 1 by n, which is going to be 1 divided by length of the total number of observations that you are having within your test set here. Okay, cool. Or we can simply call this as actual y and predicted y. This makes more sense, isn't it? This is your actual y, this is your predicted y. And we call this as MSE. So take a square root of it. It's going to be RMSE value, the root mean squared value. So we're going to return both MSE and RMSE as a tuple. We're going to invoke this function with actual y values, which are going to be y-test, predicted y values, which are going to be test spreads here, in order to obtain what your MSE and RMSE values are. So your MSE and RMSE values are going to be 328 and 18 for the given data. What is the data that's given to us? We have synthetically generated this data for about 100 different samples. And I've introduced a noise as well here so that whatever data points that we are generating do not establish a perfect linearity in between x and y. I do not want that to happen. And hence I have introduced some noise to it. Also set a random state so as to reproduce the same observations that I find for x and y and multiple runs of the code. Cool. Fine. So now we have the MSE and RMSE is obtained. So we also would want to make sure if whatever MSE values and RMSE values that we have computed are correct or not. So for that, we can always go about cross-checking by importing the relevant metrics or relevant functions associated with mean squared error as well as the root mean squared error here. There's a typo here. It's sklearn dot metrics. Okay, it's going to be mean squared error and root mean squared error. Not sure why we have this strike off. Probably that's deprecated for the version that I'm currently using. So mean squared error accepts two different arguments, which is going to be y-test as well as test predictions. And root mean squared error that we have imported also accepts two different arguments, which is going to be y-test and test predictions here again. The values that we have obtained now, that is 328.53 and 18.12, is perfectly matching with what we have computed with our own custom function called eval metrics here. Okay, cool. So we now have implemented the linear regression model by conducting the whole optimization process that we have learned. But there is one caveat to this. Here we have not necessarily looked at implementing the stopping criterion. So we are not checking for convergence if you observe closely. So we are conducting this parameter update for all of the 1000 iterations, but we have not actually conditioned any of the convergence criteria here. So I'm leaving it as an exercise to you to actually make some changes to the code so as to incorporate a stopping criterion. Okay, so as to stop the optimization process whenever you encounter that your weights and biases are not updating to the extent that you are planning to update, or probably the gradients that you are observing is near zero, you simply take the difference of the current weights minus previous weights and set a threshold. If you are observing the difference of current weights with respect to the previous weights is lesser than that particular threshold, then you stop the optimization process as a whole, stop this iterative for loop, and finalize the weights and biases at that particular point in time, and use those weights and biases in order to compute your y-preds within your predict function or predict method, to be more precise. Okay. So you also can come up with a simple plot so as to understand how good of a fit you have created now. So for that, I'm going to make use of the matplotlib module here, matplotlib spyplot module. plt.subplots is going to help me create both figure and axis objects here. So ax.scatter is going to help me generate a scatter plot where on x-axis I have x data, on y-axis I have y data, or probably I can call it as x train and y train to be more precise. I'm also going to color code them with probably green. Yeah, I'm going to provide a size of 10 and also marker as solid O, that is solid circle. So same is the case for test data here. It's going to be X test as well as Y test on Y axis. So color, I'm going to change it to blue. Marker, I'm going to update it to probably star. And finally look at coming up with a plot which has this X axis as X test and Y axis. We are going to come up with the test predictions that we have generated from the model, which represents the linear equation or the regression line that we have created so far. So the color, I'm going to have it as red color. Okay. So plt.show is going to help us generate the plot as a whole, but we have not set the X labels and Y labels yet. So ax.set X label is going to set the X label. I'm going to give it as X, and set Y label, I'm going to give it as Y here. Okay, cool. So now you clearly observe whatever regression line that you have come up with is a good fit to the scatter plot that you're observing. The stars here are determine that they are test observations and the solid circles are representing the train observations. So this is the error that you can consider for every single point. Let's say that you are considering this particular point. You're taking the difference of your actual y and the predicted y, which is laying on this particular line. So this is your error captured. So likewise, you find the errors associated with every individual observations of your test set. Let's consider a test set. So this is E1, E2, E3, so on till you exhaust all of the differences. And then you square all of them, right? And divide it by total number of observations in test set. Then you obtain your MSE. Take a square root of your MSE. You are going to obtain the RMSE. So these are the values that corresponds to the deviations that you are observing in between the actual test Y and the predicted test observations that you have deduced. Okay. I believe you have pretty much understood what I'm trying to explain here. So we have gone through the gradient descent process as a whole, different steps that are involved in the gradient descent process. We also have created this linear regression class which implements the gradient descent process, where you try to find the weights and biases, the right weights and biases, but I have not implemented the convergence criteria here, which I have left it as an exercise to you. And finally looked at predictions using the predict method. So we instantiate that particular class to create the model object, which is given as model. We fit it onto the trained data. We generate the predictions using predict method of test set. So we call this as test predictions. We use test predictions as well as the actual y-test values in order to generate your evaluation metrics. Finally build a graph so as to understand the regression line that you have come up with is pretty decent fit to the given data or not.